Okay, so this next experiment, which I've labeled number 3, should be the second major type of PVT experiment. It's called a multistage separator test, and we've already discussed this in connection with the flash calculations before, so I'm not going to give too much detail, but I will give you a few comments about the measurements and what's reported and so forth. This is the multi-stage separator test, and typically it's 2 to 4 stages. Most common, maybe in the old days, was 2 stages, where they were really trying to find out what pressure and particularly temperature of the first stage gave the most stock tank oil. Okay? Basically, you're taking a reservoir fluid mixture in single-phase conditions to the surface, and you're trying to figure out, if I've got one barrel of this reservoir fluid, how can I get the most stock tank barrels out as sellable oil? That's the purpose of the test. To some extent, so basically, this oil volume, which I'll write like this, that dependency of that oil volume on the separator temperature, but probably even more so the separator pressure of the first stage, is the reason for the test. The second would be particularly the primary gas if the gas oil ratio is large enough, let's say more than 750 cubic feet per barrel, be like 100 cubic meters per cubic meter. If there's enough gas, particularly the first stage gas, the composition of that first stage separator gas can be important, because you can extract liquids out of that, propane, butanes, and gas liquids. That can be very valuable, particularly as the gas oil ratio increases over time. So another reason would be to get the composition of the separator gases. And that's, again, primarily for estimating potential, if you add enough money to the processing of the gases, potential natural gas liquids that can be extracted. So that would mainly be C3, C4, and C5 plus. Of course, getting the general total gas volume here, which is just the sum of the 3 gas volumes from each stage. For the different stages K, this would be from 1 to 3, the gas volumes from each stage. And the ratio of gas oil ratio, this is obviously, or if it's a gas condensate, the inverse of that, the oil gas ratio. So these are the maybe in this order, the primary 3 things that are why you would want to do this test. Or the inverse of that for the oil gas ratio. Instead of composition, in the old days they would just measure the gas gravity here. That could also be used for each stage. And then for oils in particular, this would be expressed as a formation volume factor at the bubble point, which is defined, and this is again the next topic, so we're a little bit ahead of ourselves. This oil formation volume factor, and in this case we're looking going from the bubble point pressure and reservoir temperature, is how much oil volume you have at the bubble point, and basically how much it shrinks to stock tank. Okay, so if the amount of, if you start with 1 barrel, or let's say 1 cubic meter, let's say 100, because it's a lab experiment. If you start with 100 cc's of oil at the bubble point, 100 cc's of oil, and you end up with 50 cc's sellable oil at the end of the surface processing, then the shrinkage is what? Is 50% shrinkage. It's shrunk by 50%. It's shrunk by a factor of 2. Okay, you could say it that way. The formation volume factor will be, in this case, 100 cc's over 50 cc's, so that number is going to be 2. So we're shrinking the oil by a factor of 2. If the ratio was 3, meaning that we only got 33 cc's of stock tank oil, then that ratio BOB would be 3. We say that the oil has shrunk by a factor of 3. Okay? So the oil formation volume factor is telling you, as you become a seasoned reservoir production engineer, the BO is telling you the number to add at the end of, oh, the oil shrinks by a factor of, that's the number, 3. The other way to think about it is that if you take the inverse of that number, is that my 100 cc's, the shrinkage factor of 100 cc's is 0.5. It shrinks by a factor, it shrinks down to 0.5 of the volume. So that's kind of the inverse. Sometimes we use the shrinkage factor, which is the inverse of the BO. Just so you're aware of that. But the lab will report this number, and if you're interested in thinking of it in a little different way, then sometimes we call the shrinkage factor of the oil is basically just 1 over BO. Okay? That's what the judge and the lawyers can understand, and economists. And sometimes this shrinkage factor formally is defined in the SPE with a term called little b. You just use little b. Okay? So the little b is the shrinkage factor, and of oil, and the big B is kind of the volume, formation volume factor. So, okay, that's the separator test. So a couple of practical comments. It's only used today if the GOR is approximately greater than, probably, I should say less than or equal to, well, somewhere between 5 and 10,000 cubic feet per barrel. The labs will basically tell you we can't do this experiment very accurately if you're higher than 5,000 cubic feet per barrel. I mean, maybe they can, but somewhere in this range. And that would be somewhere between 1,000 and 2,000 standard cubic meters per standard cubic meter. Okay? So if it's more than that, the lab can't measure the resulting surface oil accurately. It's too inaccurate. So that would be pretty much any oil, of course, and what we would call richer gas condensates. And on our list of reasons for doing this test today, these are all kind of, there's now probably one that it helps build the equation of state PVT model. You remember this map I gave you of pressure, composition, temperature, kind of where things were going on in the reservoir and the production system? Well, these are the only data they're going to measure that apply up at the surface. And what we do at the surface in trying to extract out maximum liquids is very dependent on those calculations up there. So you're also helping to build the equation state model specifically for optimizing the surface process. And what does optimizing mean? Maximizing surface liquids. Oil, condensate, gas liquids. Okay? Propane, butane, etc. So to get that right, you need data to tune the model, this equation of state, and if all the other measurements are made at reservoir temperature is not what you have up at the surface. So you're trying to get custom data to help build this EOS model. So that would be on the list. I don't know if it would be 1, 2, 3, or 4. It's kind of like it's important. Okay.
The report for every state of separation?
Right, because what they'll report is they'll report this total, but they'll also report GOR for each stage, which would just be that gas at each stage over the final oil. That's one definition they may use, but they may use another definition which the actual separator oil volume here. So they may report it relative to the separator oil volume, or they actually may give you both.
Oh, you mean in individual GOR
For
each
stage, stage 1, 2, and 3. Yeah. And these two are not the same. You can add together if it's defined as definition 1, because they would have a common denominator, right? You could add the 3 together to get the total GOR. You cannot add the 3 GORs defined in method 2 because they don't have the same denominator. So it's more common to have this reported. Okay, so let's go into the chapter 6 and see if we can find for the oil. This gas condensate doesn't have a separator test. The oil does. Okay, it is in there somewhere. I just have to. I think. There we go. Okay. So I'll copy this in. Okay, so this actually is kind of old school because what they've done is that this table 6.7 is actually they did 4 SEP tests. Each is a 2-stage separator system. Means there's just 2 stages. Separator pressure and temperature 1. So these should actually be broken apart. This is the separator test 1. Separator test 2. And separator tests 3 and 4.
Excuse me?
Yeah.
Professor, at the unit beneath the separator pressure, it's mentioned in PSIA, absolute.
Yeah, this would probably be PSIG because of that. Yeah. It's a misprint in the book. So that should be PSIG gauge. Thanks. So what you can see is that what's changing, the only thing that changes from one to the next is this first stage separator pressure. And what they're looking for is they want to make the most oil. So they want this FVF to be the smallest possible. Okay? Shrinkage by 3, shrinkage by 2, shrinkage by 1 is no shrinkage. So you want the BO to be as small as possible. So if you just look at these numbers, 1.48, 1.47, 1.48, bang, we're in there at least close, around 100 psi. So you're going to make more oil, you're going to sell more oil if you operate the separator, first stage separator pressure at 100 psi instead of 50 or 200. Now, okay, 1.48, 1.47, what the hell do you care? All right? Yeah, it's easy to think that. Let's just make a little calculation. Okay, so let's say we've got an oil rate from a well. Do we want to be in the North Sea? Want to be in Oklahoma? 1,000 barrels per day. That's a rinky-dink, horizontal well, multi-fractured well in Oklahoma, Anadarko Basin. Stock tank barrels per day. With 50 psi gauge separator pressure. Okay? It's making 1,000 barrels per day at that. We've got $30 per barrel. So sad is it? Okay. Okay. So, what will be the oil rate with 100 psig separator pressure? Okay. What will that be? Should be 1,000 times the BOB for the 50 psi over the BOB for the 100. We agree on that? So that's 1.481 over 1.479. 0.74. Can somebody give me that number? Instead of 1,000, it's
1,005 there.
how much?
1,005.
1,005 stock tank barrels per day. Okay, 5 stock tank barrels per day times 365 days, okay, times $30 per barrel. How much is that?
54750.
5, 4,
7
7,
5 0.
50. Okay? What the hell is going on here? I don't want to see emails. Okay. That's US dollars. Is that correct? Anybody else get the same number? That's the starting salary for a young engineer if they can get a job in the United States. That's probably a starting salary here if you can get a job here.
Annual.
Annual salary.
Yeah.
Yeah. So, does it matter? Well, does your salary matter? Okay, that's all it takes to figure it out. So, okay. So you're basically going to be making 5 barrels a day if you get a job. Okay, which. Okay. Well, it used to be $100,000. I mean, you probably make a little more if you can get a job. So, but it's, of course, it used to be $100 a barrel too. So, and all of a sudden we're okay. So it does make a difference, and for a big oil company, and they own 600 of these wells, and it starts making a difference to the company as well. Okay, at least it should make a difference. Okay, so that's surface separator. Okay, so the third type of experiment, we're kind of running out of time, but I'll get started on it. It's essentially the same procedure as this experiment, because in the multi-stage separator test, what do we do at each stage? What we do at each stage is that we remove all of the gas and we're left with the oil. We bring the resulting oil to a new stage, equilibrate to gas and oil, remove all of the gas, we take the remaining oil, flash it down by itself. That's the procedure. Okay, you're removing all the gas at each stage. So this next experiment, in our list of 4, we call it the differential liberation. Experiment. I call it DLE, but it's just deal. This is conducted only for oils. And it's the same process, if you will, as the SEP test with a big butt. The temperature at each stage remains the reservoir temperature, okay? The temperature at each stage remains equal to the reservoir temperature. Okay. So the whole experiment is going on at reservoir temperature. Okay, the purpose of this experiment, and there's going to be, in the number of stages, is going to be not 2 to 4, but it's probably going to be 5 to 10. Okay, If it's a low bubble point, there won't be 4 or 5 stages. If it's a high bubble point, it might be 7, 8, 9, 10 stages. Okay? 10's probably pushing it, but the real purpose of this experiment is to first study the reservoir oil it's going to take too long. We don't have enough time. So, it's to study how the oil density varies as a function of pressure below the bubble point. There's a parallel experiment that's run. It's also a differential liberation, and we might as well say it's done at the same time. It's just that it's not, but it's essentially the same experiment. We're also interested in how the viscosity varies at pressures at and below the bubble point. I know, this is an engineering. What do we need to know as engineers? Density, viscosity, and what else? We got a mixture. You know, if you're a reservoir engineer, you're down in the reservoir. You got a mixture. Okay? You want to know what? I've got a mixture. Curtis, you're the PVT guy. Tell me something. I'm going to do calculations in the reservoir. What do you need to know? No? Huh? No? I'm just an engineer. I don't know about petroleum engineering. I don't know what a volume factor is. We're talking about learning in high school. The terms that we learned in high school, what we've been talking about. We need to know if there's 1 or 2 phases. Why? Because if there's 2 phases, you learned a couple of years back when Ola Torstetter told you about relative permeability, right? That the mobility, which is what gets you the oil rate and the gas rate, is the mobility, the permeability of a phase is proportional to what? The percentage of that phase in the pore. So if it's only oil, it's got a higher permeability. If it's only half oil, if oil shrunk by a factor of, if it's half oil and half gas, then the permeability of the oil and gas drop. Do they drop linearly? They drop as the saturation of the phase to a power of 2 at the best, 3, 4, or 5. Okay? To a power of, on average, 3. That means that if the oil shrinks, its permeability shrinks a lot more. And if the permeability shrinks a lot more, the oil rate gets lower a lot more. And that is like what's keeping our jobs, if we can get a job. So we need to know the number of phases, and we need to know how much of each phase. Okay? So that needs to be in there. How much does the oil shrink? How much the oil shrinks? How does the oil volume, relative to what we start with, change? That's the oil shrinkage. It's because that's effectively oil saturation, and permeability to oil is proportional with oil saturation to a power N of about somewhere between 2 and 5. And that's a big deal. Oil rate, which pays your salary, is directly proportional with KO. Okay? So you'd like to know how the oil shrinks, and it's expressed, basically they measure how the oil shrinks. They also want to know the oil density, and they want to know oil viscosity. Okay. The only other PVT property like a hardcore chemical engineer needs is composition of the oil. For maybe some strange reason, the reservoir engineer doesn't care about the composition usually, but they might want the composition as well, but probably not. They basically don't really need it. Okay. And they don't measure. So these are the main things that we want. Oil density, oil viscosity, and how the oil shrinks. Likewise, you want to know A prime, the same for the gas. And it's not less than or equal to, because at the bubble point, we have infinitesimal, and when it's infinitesimal, we don't care what the viscosity is, right? So it's below the bubble point, the gas properties. Now, effectively, because Sg is basically 1 minus SO, right? Forgetting the water, okay? It's in there, but it's basically, if you know the oil shrinkage, you know how much gas volume is being, okay? But what you would like to know is how much gas is released. How much gas is released as we go below the bubble point? Okay, the released, the gas, not gas is released, but how much gas is released. And then finally, we might be interested, and probably more so, in the composition of the gas at pressures below the bubble point. Okay, because that gas starts larger saturation, the gas starts flowing more and more because the gas saturation is increasing, and the composition of that gas is important because it's carrying with it some of the oils that we're going to, or some of the components that we're going to make turn into a liquid at the surface. So you'd like to know the composition of the gas, because what gas flows, it's not as good as oil flowing, but you got to take what you get. So you want to know how much propane, butane, C6 plus heavy stuff is in the gas, because we'll extract that out as liquids at the surface. So you might be interested in the gas composition. And that's what this experiment, differential liberation, is trying to provide.
So this gas release will not be equal to the gas release we have at the separator.
No, it's the gas released in the reservoir. You want to know the gas released in the reservoir, basically. Yeah. Now, some of that will make its way to the surface, but it's really looking at how much gas comes out of solution, how many moles of gas come out of solution. And if you know the moles that come out, you know the gas density, and you know the gas molecular weight or composition, then you know basically the volume of the gas but at reservoir conditions. Okay, so this is the differential liberation experiment. Basically, we want to know PVT properties at reservoir conditions. TR and P less than or equal to bubble point. Nothing at all about the surface. Nothing at all about how much oil we're going to sell at the surface. Nothing. Okay? It's only how the reservoir properties change with pressure. That's all we get out of this experiment. So the experiment's very simple. Okay, it's a very simple experiment. You can actually use a blind PVT cell because you actually get the gas volume, because you take it away, you know how much gas volume it is. I mean, in other words, if we start at the bubble point here, say at the bubble point, so it's only oil, and then we make the cell larger. While it's in the cell, we don't know what's gas and oil, right? But what we do is that we remove this at pressure. This would be pressure 1. This would be pressure 2. At this pressure 2, we remove that so we know the volume of gas because we removed it, okay? We remove it at that pressure. So we know this volume of gas at 2. And once we've removed everything, what's left in the cell, we know that. So we don't need to visually see it. We actually just, we measure them directly because we're removing all the gas. So basically we get that and we get that.
How do they know that exactly when the gas is?
Yeah, so at least the way, while I was still in the PVT laboratory, before they kicked me out, I actually had the pleasure of staying alive and doing experiments like this. So what happens is that you're moving this pump and removing the gas, and the pressure gauge is a big old pressure gauge. It's at 200 bar, okay, and you're moving the pump, you're moving the gas out, everything. And what happens is that when the last bubble of gas leaves the cell, that pressure gauge pops up, and then you shut the valve. So it's because this compressibility effect. So you have to be quick, and you're doing the pump very slowly, but you're watching the manometer and moving it out, and then as soon as the manometer kicks, then you stop. So it's a visual thing. Okay. So we use a blind cell. It's a simple experiment. The gas that's removed, you basically take this through a flash process to standard conditions. You go through a gas meter to estimate basically the equivalent surface gas volume that's been removed. Typically, we don't worry too much about the liquid that condenses from the gas in most experiments. But basically, we use a gas meter here. That gives us approximately the number of moles of gas that have been removed. When you flash it, there might be some small amount of flashed oil. This is usually ignored or not measured very accurately, but it may be there. But this surface gas converted to surface volume of gas and the surface moles of gas. If you add these two together, you get the moles of gas removed. Okay, so if you got the volume, the moles, the pressure and temperature, you have the Z factor. Okay, so you've got the moles, the volume, and the pressure, so we can calculate the Z factor of gas, and that's going to be reported by the lab. So that's equal to the pressure, volume of gas removed, R, reservoir temperature, and missing something, number of moles removed. And so they calculate that Z factor. Okay, so you can, this is enough to get you started reading chapter 6. On Tuesday, we'll finish up with this and then do the constant volume depletion, then we'll be done with the experiments. So if you want to kind of be caught up in reading, just read chapter 6. Any questions before we, good luck playing detective.